Greetings everyone, I'm Tom Irvine, and this is another edition of the webinar series, the Shock and Vibration series, which is being graciously sponsored by the NASA Engineering and Safety Center, NESC, and thanks once again for Dr. Curtis Larson for making this webinar series possible. Well, today we're going to be talking about Fourier transforms, and Fourier transforms it's a wonderful tool for helping us resolve signals. It helps us to be able to take a time history signal and to deconstruct it into its spectral components. And you're going to be seeing that in the upcoming slides here. Also, this webinar unit is going to be a little bit different than some of the others in that we are going to have to concentrate a little bit more on the theory, the underlying theory, than we normally do. This whole webinar series tends to have more of an emphasis on applications with the corresponding underlying derivation given in papers which are available at the blog where these webinars are posted, the Vibration Data blog, that is, the WordPress blog. But let's go ahead and dive right in here. So Fourier transforms. So here's some interesting research that was done by a Professor Alan M. Nathan from the University of Illinois a few years ago, and he was interested in baseball bats. So when the baseball bat strikes a ball, the ball effectively is applying a force impulse against the bat. I guess you could say vice versa as well. So we get a forced response. So on the left side here, Dr. Nathan has a time history plot. Now, he identifies the y-axis as r, and I'm not sure if that's acceleration, velocity, or displacement, but let's just go ahead and go with this time history. And again, this is the blue curve, so the x-axis is time in milliseconds. And either through, whether this is test data or just pure analytical data, synthesized data, I'm not sure, but let's go to the red curve on the right, and this is the fast Fourier transform. Now, today we're just talking about Fourier transforms, but in upcoming units we're going to be talking about the fast Fourier transform, which is a special case of a Fourier transform. But the point I want to get to is this red curve takes this blue curve, the blue time history, and it resolves it into spectral components. So we see at 179 hertz, we get the fundamental bending mode of this baseball bat. Now the bat effectively is behaving more or less as a free beam. Then there's a harmonic, a non-integer harmonic that occurs at 582 hertz, and then there's another one at 1181 hertz, and then so on, some higher modes as well. So one of the tasks we have at hand is we need to come up with a mathematical function, a transformation, in other words, to get from the time history on the left to the spectral function on the right. And if we know what the spectral function is, that helps us to understand. It can help us to understand, for example, the natural frequencies of an object that an object is undergoing in its response, or in some cases. It will also help us to identify the forcing frequencies. For example, if we have a helicopter or some machinery with rotating or reciprocating parts, we can pick out the forcing frequencies or the imbalance frequencies from the rotor. Moving along, so we're going to have to sort of take a step back and look at the big picture here, and we're going to have to take a look at what the mathematicians tell us about Fourier transforms, because mathematicians have a very theoretical approach, and they have a set of formulas they use both for a Fourier transform and the corresponding inverse Fourier transform. And the mathematicians' format for Fourier transforms are not going to work for us as engineers as taken just straight out of the box. So we're going to have to spend a little bit of time with the mathematicians' Fourier transforms, but then we're going to modify those for practical engineering purposes. So we're going to have to start with some equations. And just before we get into that, though, let's think about signals. So In our previous unit, we talked about random vibrations. So we can have random broadband vibration, or in some cases narrowband. The vibration can be stationary. So broadband random stationary would be one type of vibration that could occur. Or we could have something like a pure sine function, a pure sine oscillation. And as it turns out, a lot of the signals we actually measure tend to be some combination thereof. So we can have a broadband white noise, but it can have a sinusoid superimposed upon it, or sine sweeps, or narrowband, or anything imaginable. So one of the uses of this Fourier transform that we're going to be developing in this unit is to help us resolve the characteristics of the signal in the frequency domain. So let's just go with an example here. This is a sample acceleration time history. And one of the things we want to do in this course series is develop some critical thinking skills about signals. So as we look at this signal, it's not a pure sine, but neither is it random. There seems to be some repetition, some sort of a pattern repetition going on of some sort. And I'm going to go ahead and I'm going to short circuit this whole process. I'm going to tell you what this signal is, because it turns out this signal is a deterministic function. It can be expressed in terms of a neat and tidy mathematical equation. And that equation is going to be composed of actually 3 sine functions. So here's the mathematical function for the previous time history. So we have our 3 sine functions, and the corresponding amplitudes are 1, 1.5, and 1.2 in units of g. The corresponding frequency in units of hertz are 10, 16, and 22. Now, I could have specified a phase angle, but for this series of sine functions, the phase angle is 0 for each of the 3 cases. So what we need is a spectral function to resolve these frequency and the corresponding amplitudes in the frequency domain. So right now, I'm just going to call this a spectral function. Now, later on, we're going to call this a full amplitude discrete Fourier transform. But for right now, it's just a spectral function. So along the y-axis, we have acceleration in g. Along the x-axis, we have frequency in hertz. And there are 3 spectral lines duly noted with corresponding frequencies of 10 hertz, 16 hertz, 22 hertz, with their amplitudes, respective amplitudes of 1g. And then we have a 1.5g and 1.2g. So this makes sense to us. This is something we feel good about, because this helps us to understand the underlying properties of that time history, its underlying characteristics. And this gives us some information that's useful for design and test purposes. For example, if that were truly, the previous mathematical function were truly the forcing function or the base excitation function, we might want to make sure that it would be good engineering practice to make sure the natural frequency of our structure were well separated from any of those 3 peaks. So now we're going to get into the real complex theory in the mathematician's world. So this is the mathematician's textbook Fourier transform. So the Fourier transform, in this case, we have uppercase X as a function of frequency f. For a continuous time series, lowercase x as a function of time is defined as, okay, now here we have an integral. Now the time history, the continuous time history, goes right here. It's embedded in the integral. There's this weighting function, and it's the exponential function minus j. Well, j is the square root of minus 1. 2 pi frequency typically in hertz, and units of time typically in seconds. And then we integrate with respect to time, and we integrate over the time domain from minus infinity to positive infinity. So the time domain signal is assumed to be continuous from minus infinity to positive infinity. Now the resulting Fourier transform is also going to be continuous, and it's going to be from minus infinity frequency units to positive infinity frequency units. So this is an abstraction for us, for engineers, for all sorts of reasons. One of several reasons is that our time histories, they don't go from minus infinity to positive infinity. We have time histories that are limited. They're finite duration. If we go out and take an accelerometer reading on a vibrating object, that could be for 10 seconds or 60 seconds or maybe 2 minutes or whatever, and we're probably going to start at time 0. We'll probably call our starting time time 0, and then at some point we're simply going to end. Well, and then another situation is we take readings from accelerometers or pressure transducers or force gauges, whatever you might have. We're going to digitize that data. So we're not going to have continuous time series for engineering purposes. We're going to have digital time histories. So that's just a few complications here. Okay, here's another complication. Integrating with respect to time, in some sense, this is like a multiplication of sorts. So if we have acceleration in g for this time history, by the time we carry out this integration, our Fourier transform will have units of g second. Well, what's a g second? How do we design and test for a g second? What is that? Is that some kind of a velocity unit? And the simple truth is, I don't know. It doesn't make sense to me. Well, that's just another layer of complexity that we're going to need to resolve. Another thing we need to think about is that if we have a Fourier transform, we can also have an inverse Fourier transform. And to take an inverse Fourier transform, we exchange the time domain function with the frequency domain function. Actually, I'll show you that in the next slide. So if we have a Fourier transform, we have an inverse Fourier transform pair. So here we would put the Fourier transform here, and we get the time history back out. So if we take the Fourier transform of a time history, then turn right back around, take the inverse Fourier transform, we get our original time history that we started with. Well, here's another complexity. Every time we take that accelerometer measurement, or force transducer measurement, or strain measurement, our time history is real. It is strictly real. Well, going through this process here where we introduce this j, the square root of -1 here, this renders the Fourier transform as complex. So you can think of complex as having real and imaginary parts, or you can think of complex as having magnitude and phase. And if we know real and imaginary, we can calculate magnitude and phase, or vice versa. So we start with our real time history. We get our complex Fourier transform out here. So then what happens? We take our complex Fourier transform, plug it back here, back calculate where our time history is. Well, now our time history is complex. It has real and imaginary components. Well, who's ever heard of a time history with an imaginary component? I never have. Maybe you have, but I just never have. As an engineer, I would not know what to do with an imaginary component in the time domain. Well, it turns out that this is one of the easiest hurdles for us to jump over, because it turns out if we have a real time history, which our measured time history always is, and we go through this inverse Fourier transform, well, as a matter of fact, we do get imaginary components for the time domain, but they are all 0. So the imaginary components of the time history is all 0. The non-zero part is all real, so we're okay. If we have a time history with an imaginary part that's all 0, we can just chop that off. We can just ignore it. So we're okay in that sense. But we still have some work to do. We got some things we have to clean up here. We have to modify this. We need something practical for engineering purposes. Just a little bit of a review. Hopefully you remember complex numbers and real and imaginary, and magnitude and phase. So let's say we have a variable v. It's a complex variable, and it's made up of a real component A. Once again, J is the square root of -1. Then we have the imaginary component B. So if we want to take the magnitude, it's the square root of the sum of the squares. If we want to take the phase angle, that's the arctangent of the imaginary component divided by the real component. So if we know the complex form with real and imaginary, we can calculate magnitude and phase. There's also some formulas whereby if we know magnitude and phase, we can take some sines and cosines and get back to the complex format. So again, this is sort of a repeat of what I've already said, but it's good to review it. Practical measured time histories are always real. Note that the inverse Fourier transform calculates the original time history in complex form. The inverse Fourier transform, which is our reconstructed time history, will be entirely real if the original time history was real, however. So again, the imaginary components will all go to 0. Well, we're still in the realm of our mathematician's textbook Fourier transform here. So I'm going to say that the simplest oscillating function that we can deal with is just a pure sine function. So here's a time history here. Now some of you might take an exception and say, oh, well, what about a sawtooth pulse or a rectangular pulse or whatever. But now, just go with me on this, that the simplest oscillating function is a pure sine. So again, we have a pure sine here. It's got amplitude A. This is going to be a 0 phase angle case. 2 pi, the frequency is f hat, and then we have time t here. So what happens if we take a mathematician's Fourier transform of a pure sine function? Well, since it's a pure sine and since it has 0 phase, the Fourier transform will be strictly imaginary. So the real Fourier transform will be 0 across the board. So I'm not going to show you that plot. I'm just going to show you the imaginary. So here we have the f is equal to 0 line. This is the frequency. And some funny things are going on here. One thing we note is that this imaginary Fourier transform, it's anti-symmetric about the f is equal to 0 line. So that's noteworthy. And it seems like half the amplitude is getting deposited down here with a negative sign, and the other half the amplitude is getting deposited here at negative f hat. So this frequency, I need to go back and fix this slide, is f hat, and this is minus f hat. Well, a couple of odd, strange things going on here. First of all, as engineers, how do we design and test for negative frequencies? And the truth is, I don't know. I've never had to design, test, or analyze for negative frequency. So this is an abstraction that just doesn't make sense to us more concrete-minded engineers. And here's another complexity. Instead of showing clean spectral lines, I'm showing these lines with arrows. Well, what do these lines with arrows mean? Well, and then I've got this funny little Greek letter here. It's a delta function, and more particularly, it's a Dirac delta function. So who among you as an engineer has ever had to design or test for a Dirac delta function? Well, not me. I wouldn't know what to do with it. And I guess the mathematicians say, well, a Dirac delta is not even a true function. It's some sort of abstraction. Somehow it's 0 everywhere, but if you integrate it, the area is 1 or infinite, or I don't know. It's some odd thing. And you can read more about Dirac delta functions on your own. So this is, I mean, the mathematicians love this stuff. They love it, and good for them. But for engineers, this just doesn't work for us. So here's just some general notes, and these apply to any signal, whatsoever, whatever signal you might have. The real Fourier transform is always symmetric about the f is equal to 0 line. The imaginary Fourier transform is always anti-symmetric about the f is equal to 0 line. So again, the anti-symmetry shows up like this. So this is a minus a over 2 times this Dirac delta. This is positive a2 times this Dirac delta. So we need something practical. And this is actually going to take us several steps to get something that's practical for engineering purposes. So again, our sensor, our accelerometer, whatever sensor we might have, it returns an analog signal. And in the old days, that signal would be just fed into a digital, not a digital, but an analog oscilloscope. And the analog oscilloscope would just show would show what appears to be a continuous line. But nowadays, we do something different. We take the signal and we digitize it. We feed it into an analog to digital converter, and we get this digital data, and then we display that on our computer screens. And so one of the things we need to do is take our mathematicians' textbook Fourier transforms and modify them to accommodate digital data. And this is one of the important dividing lines between mathematicians and engineers in regards to this Fourier transform methodology. So we're going to come up with what we call the discrete Fourier transform equations. And this is an intermediate step. It's not our final destination. So here's our Fourier transform, and now we've changed the integral into series. Well, a series format can accommodate digital data, obviously. And this is our time domain signal here. It's going to have this index n. So our time history now is going to have a total of n points. So our time history is finite, and it is digital. And that's important to us as engineers. And here's this exponential weighting function. Again, j is the square root of -1. 2 pi over n, n's a total number of points. N is an index for the time domain. And then k is sort of an outer loop index for the frequency domain, the Fourier function, Fourier transform. So there's another advantage to doing this way. We're no longer integrating with respect to time, or we don't have a delta t here, but instead we divide by the total number of points n. So in some case, what we're doing is taking a weighted average of the time domain for each inner loop, and we do this for each frequency of interest. So another great thing about this is, let's say we have acceleration in g. That's our time domain input signal. Our Fourier transform will now have units of acceleration in g, and that is welcome news for us as engineers. And if we have a Fourier transform, we can always have an inverse Fourier transform. So Fourier transform goes from here to here. Time domain function comes out from here, gets deposited down here. The series is the same format, only got a bit of an index change here. We're going from n here, which is the time domain index, whereas from here we're going from k, which is the frequency domain index. And both the time history and the frequency domain functions are going to have a limited number of points, each equal to n number of points. So they're going to be finite, and they're going to be digital. And this is good news for us. We're so much better off now for engineering purposes with this type of a format. Something very important, a little bit of a side note, but this is going to be so important for signal processing. We have a parameter called the frequency increment, or you might call it the delta frequency, or the frequency step. And that's equal to the time domain period. Now when I say time domain period, that's the total duration t of the measured signal. So our frequency resolution, or frequency step, delta f, is equal to 1 over t. And this is also the smallest frequency we can resolve in terms of a sine function. So let's say we measure data for 10 seconds. That means our frequency step is going to be 1/10 of a hertz in our Fourier transform. So another way to think of this is, let's say we have a sine function, and its period is exactly 10 seconds, and we measure exactly for 10 seconds. So we measure exactly 1 cycle of that sine function. Well, in that case, delta f would be 1/10 of a hertz, which is the frequency resolution of our Fourier transform, which is also the frequency of that 1 cycle sine function over 10 seconds. So another way of thinking of delta f, that's the smallest frequency sine function we can identify. And one of the points of this, if we need finer resolution, we should take a longer and longer time duration. So in that sense, the longer the time duration we measure, the better off we are. But of course, there's some practical limitations to that. If we're measuring a pyrotechnic shock event, and it only lasts a matter of milliseconds, then we're going to measure for a couple of milliseconds. We might allow some quiet period thereafter, but we're not going to take a pyrotechnic shock that lasts milliseconds and measure it for 10 hours. It just doesn't make sense. But if we have more of a steady state type stationary vibration, then it is very advantageous to take longer time domain, longer duration in the time domain measurement. Okay, an important concept here is the Nyquist frequency. This is going to be making several appearances over the next couple of webinar classes. So the Nyquist frequency is equal to 1/2 the sample rate. And Shannon's sampling theorem states that a sampled time signal must not contain components at frequencies above the Nyquist frequency. Otherwise, if we violate that rule of thumb, we get an aliasing error. So we're going to be talking about aliasing errors and precautions for preventing aliasing in some upcoming units. But right now I just want to take a little break and show you just a fun little video clip that I took a while back. So many of you live in homes or an apartment or townhouse where you have a ceiling fan. Now I know in some places where it gets hot, you're more likely to have a ceiling fan, maybe not so much in colder weather areas, but here's a ceiling fan. And the way a lot of these ceiling fan works is sometimes we want the ceiling fan to take area at the top of the room and to push it down. Or other times, depending on the time of year, the temperature and all that, we want the ceiling fan to pull air up and redistribute it that way. So we can go to a little control box mounted on the wall, and we can push one button for the ceiling fan to oscillate counterclockwise and another for it to oscillate clockwise. So we have control over that. But the control is going to make us decide one way or the other. Well, this is a previous home that I once lived in, and I want to show you this very special ceiling fan I had in this home. So I'm going to push this button here. This is a magic ceiling fan. Now I had to pay extra money to get a ceiling fan that could do this operation. So the ceiling fan can instantaneously change its direction of oscillation. Well, that's all, of course, kind of a funny joke, because what we really have is aliasing going on. We have optical aliasing going on because the frame rate is too low to adequately capture the motion. And as we look from top to bottom, the ceiling fan was always going counterclockwise. But just as an optical illusion, in some cases it looked to be going clockwise. And just another piece of the puzzle here, what I did is I actually ramped the ceiling fan up to a steady speed, then almost immediately ramped it back down. So the ceiling fan was undergoing angular acceleration the whole time. Well, this can happen in our data too. We'll talk more about that later on, but for now I just want to start thinking about Nyquist frequencies and about aliasing effects that can occur. And we'll cover this in earnest later on. So now we have our discrete Fourier transforms. And again, we're sort of at an intermediate stage here. We're not to our final Fourier transforms. But let's go back and reconsider a pure sine function. It's going to have an amplitude of 1g, 1 hertz frequency, phase angle 0. Now I'm only going to show you the imaginary Fourier transform, because for this special case with 0 phase angle for pure sine, the real component of the Fourier transform is 0, so it's not even worth plotting. So here's our imaginary Fourier transform. Along the y-axis we have acceleration in g. Along the x-axis we have frequency in hertz. Now this is 16,384 points in this time domain signal as measured. And when I say measured, this is all a numerical experiment. 32 samples per second. The delta t, the time step, is 1 over the sample rate, so it's 1 over 32 seconds. Time history was taken over a duration of 512 seconds. Our delta f, our frequency step, is 1 over 512 seconds. That's 1 over the measured duration. So that's the smallest sine function we can resolve in terms of the smallest frequency of a sine function we can resolve. Well, in this case, we have 1 hertz, which is well above that delta f, so we're in great shape. So let's see, what's going on with this plot? Well, 32 samples per second, that's numerically the same as the highest frequency of our Fourier transform in hertz. And it's more proper to have sample rate described in terms of samples per second. But a lot of times we would say the sample rate in hertz, and that's okay too. It's a little bit crude, but that's okay to call sample rate in units of hertz if you want. The Nyquist frequency, that's half the sample rate, so it's at 16 hertz. Well, we note something here. We get 2 components, and again we're having this anti-symmetry thing for the imaginary Fourier transform. In this case, the anti-symmetry occurs about the Nyquist frequency. So we have half the amplitude deposited here at 31 hertz, and the other half of the amplitude deposited here at 1 hertz. So what does this tell us for engineers? Well, does this mean if this is our expected environment that our test article needs to undergo either in test or as field environment? If that's the case, does that mean not only do we need to design and test for 1 hertz, but we also need to design and test for 31 hertz? Is that what this is telling us? At first glance, it appears that that's the case, but the true answer is no. So what if let's just do a thought experiment here. What if we doubled the sample rate from 32 to 64 samples per second? Well, if we go to 64 samples per second, then our Fourier transform would go up to 64 hertz. And instead of being at 31 hertz, the spectral line would be at 63 hertz, which is 1 hertz less than the sample rate frequency, which is also the maximum frequency of the Fourier transform. So what do we have here? Is this some manifestation of Heisenberg's uncertainty principle, where the manner in which we observe something somehow metaphysically or physically changes the thing itself? Well, this is all kind of an abstraction. And the way we're going to solve this for engineering purposes is, first of all, we want a clean 1G line at 1 hertz. So the fact that we have only half the energy here, that's troublesome to us. That's inadequate for our purposes. So from here on out, every time we plot a Fourier transform, we're only going to go up to the Nyquist frequency, and we're going to stop. So the second half of this plot, we're going to cut off. Now, what we're going to do next, you can think of in 2 ways. One way to think of this is we're going to take this energy up here, fold it about the Nyquist frequency, and combine it with the energy here, so we get, we take absolute values, add them together, so we get a clean 1G, 1 hertz spectral line. That's one way. That's probably the more proper way to think of this. The numerically equivalent way is to say, well, we're just going to forget the right half altogether. We're just going to take the absolute magnitude and double it. If we take the absolute magnitude and double it, well, we get a nice clean 1G, 1 hertz sine function, and then we're good to go. We have something useful for design and test and other engineering purposes. So let's see, I kind of covered this one already. In this case, the sine function from the previous plot had a frequency of 1 hertz. The total number of cycles is 512 with a resulting period of 512 seconds. Again, the Fourier transform of a sine wave with 0 phase is purely imaginary. It's also it's anti-symmetric, and the real component, which was 0, was not plotted. Okay. So let's talk about spectrum analyzers. So the spectral analyzers we use for engineering purposes, and wouldn't it be nice if mathematicians could get their hands on spectrum analyzers and develop some empathy for us as engineers? But anyways, so typically our spectrum analyzers are going to represent the Fourier transforms in terms of magnitude and phase rather than real and imaginary. The spectrum analyzer is only going to show 1/2 the frequency band, do the symmetry relationship. That's another way of saying we're only going to go up to the Nyquist frequency. The spectrum analyzer may either represent the half amplitude or the full amplitude of the spectral components. So when I say half amplitude, the spectrum analyzer might just cut off the second half of the path of the plot, I should say, and only show a half G at 1 hertz. That's called a half amplitude. But the more common and the more useful convention is to represent the full amplitude, where effectively we just take twice the magnitude of the components. But let's just make sure that whatever algorithm we're using, whatever data acquisition system or spectral analyzer we're using, we understand the convention, both in terms of Nyquist frequencies and amplitudes and all that. So we're gonna make what I call the full amplitude version of the discrete Fourier transforms. So we're going to take our previous formulas and just modify them a bit. And the case at 0, at frequency index 0, you might say the case at 0 hertz, or some people say the case at DC, but 0 hertz is what I'm going to call it, is a special case, and all we need to do is take the magnitude at 0 hertz. And another way of thinking about this is we're just going to take the average of all the time history points, and that's going to be the spectral components at 0 hertz. Now, for non-zero frequency spectral components, in other words, all the components above 0 hertz, we're going to take our previous formula, and we're just going to take twice the magnitude. And this term here is a way of showing we're only going to go up to the Nyquist frequency. So go up to the Nyquist frequency, it's half the sample rate, and stop. We're done. So let's go back and so remember our previous sine function. So we have a 1G, 1 hertz sine function here. And what do we have? We have a full amplitude, one-sided discrete Fourier transform. Acceleration G, frequency in hertz. This is using those formulas I just presented. Again, we have 16,384 points. The sample rate is still 32 samples per second, but now we're cutting off at 16 hertz. That's a Nyquist frequency. And I am showing a clean spectral line, 1 hertz, 1G. Finally, we have something that's useful for us as engineers. This is something we can design to, we can analyze, we can test to this. This is something that of great benefit to us. So that's good news. And do you remember that the time history I showed you earlier, where I said, oh, we've got this time history and it's acceleration G versus time in second, and it's really just 3 sine functions, and I even showed you the mathematical formula for it. So if we go back and take the full amplitude, one-sided discrete Fourier transform of that signal, we get acceleration G and frequency in hertz. And in this case, our delta F is a bit wider here. It's just the inverse of 2 seconds, so we're getting a point every 0.5 hertz. And the convention is to connect the dots, like you remember the childhood dot-to-dot puzzle. So we connect the dots, and these are not true sawtooth pulses here. Rather, we have a 0 point here, and then we rise up, and we have our actual discrete point here. So it would probably be more honest to show this as a bar chart, but the convention is to connect the dots. So here we have 10 hertz, 1G. We've got 16 hertz, 1.5G. We've got 22 hertz, 1.2G. And that agrees with that mathematical deterministic formula I showed you a number of slides ago. So let's go ahead and just do some little exercises here. We've got some, and I'd like you to do these as homework exercises, but I'm going to go ahead and just show you how to do these in class, and then just please go do these on your own. And I'm going to have to show you a few things here. First thing, let's say we've measured a duration of 20 seconds. So what is our frequency resolution in our Fourier transform if we measure for 20 seconds? It's going to be 0.05 hertz. That's the frequency in hertz for a 20-second duration. And that's a very important equation. It's simple, but it's an important equation. Please keep that in the back of your mind. We're going to be coming back to that. Now the next thing we're going to do is we're going to play around with some Fourier transforms. So the first thing we're going to do for, well, I should say the next exercise, we're going to generate our own sine time history. Now, in this class, there's two ways we like to use data. Sometimes we have measured data. I've got measured data samples. Other times we like to make up our own data. So we're going to make up our own data. So we're going to generate a sine time history. It's going to have amplitude 7, frequency in 2 hertz, 100-second duration. Sample rate is 100 samples per second, or if you like, you could say 100 hertz. So the main software package we use in this course is the Vibration Data GUI package. And this package it's a continual work in progress. It's up to version 3.8 and rising. And please download the newest version from my blog. And we're going to, well, what I'm doing is I continue to add new functions, and also occasionally I fix or repair different bugs that I find or some of my students point out to me. Let's go ahead and generate a signal. So we begin signal analysis. This is going to be a sine function, so we set amplitude 7. We'll keep the phase angle at 0. Duration, it's going to be 100 seconds. It's going to be 100 hertz sample rate, more properly 100 samples per second. Frequency 2 hertz. Let's go ahead and calculate this. So we get our sine time history as expected. Okay, let's go ahead and save this. So we're going to save this. I'm just going to call it sine. This is going to be for the internal MATLAB workspace purposes. I'm going to call it sine. So I'm going to return. So we're going to take a Fourier transform. So we go to Fourier transform, begin signal analysis. So we've got a preloaded in MATLAB, and again, this script, I should point out, this script calculates the Fourier transform of a time history. The input array must have 2 columns, time in seconds and amplitude. So our preloaded MATLAB array is just called sine. We're going to plot it up to 10 hertz in this case. We're going to be covering windows and handing windows in our next unit. But for now, let's just go ahead and say mean removal yes. And actually, this signal already has a mean it already has a mean value of 0, so it doesn't really matter. But we'll go ahead and say yes. And in window, we're just going to call this a rectangular, or use a rectangular window. And the rectangular window leaves the data unmodified. But more about that in our next webinar unit. And we'll call this acceleration in G for our y-axis unit. And we're going to calculate our Fourier transform. Yeah, it's going to take a few seconds here now. Later on, we're going to be learning about fast Fourier transforms that can do this calculation much more quickly. But for now, we're just going to stick with the regular slow Fourier transform. So on this plot here, I get magnitude and phase, and I get a nice clean spectral line of 7G at 2 hertz. Well, that's how we design the signal, the sine function. Amplitude 7, frequency 2 hertz. So we get a clean spectral line, magnitude 7 at 2 hertz. So that's happy news. That's good. We're not so much interested in the phase angle in this case. It turns out that exactly 2 hertz, the phase angle is 0. And at other frequencies, there's no single present, so the phase angle doesn't have any meaning, really, at frequencies other than at 2 hertz. Now, sometimes we like to look at magnitude and phase. Other times, we just like to look at magnitude. So in this case, we get a clean spectral line, 7 Gs at 2 hertz. And the program even tells us what the frequency is, where the maximum peak occurs. So we are happy campers. This is good. All is well and good, and we've got a good tool here for resolving sine functions. Later on, we're going to see that there's some cases where the Fourier transform doesn't work out so well. But for now, in the world we're living in right now, it just works out great. We're going to revisit some data from previous webinar units. So we had some previous webinar units where we looked at some measured data. We looked at the tuning fork data. I think that's the very first signal we looked at. And with some of this previous data, we'd do methods like, okay, let's count the peaks and divide by time and get what the natural frequency is. We did that. And then we also found out we had a curve fitting program where we could do time domain curve fitting, and we could apply textbook functions to match up with our measured data. And we found that once we came up with a textbook function that matched our data, we could extract things like frequencies and amplitudes. And for the case of the drop transient, we looked at damping as well, and phase and so on. Well, now we're going to take our brand new Fourier Transform tool, and we're going to apply this to data we've already taken a look at before. So I'm going to click on here, and the first one I'm going to call up is tuning_fork. Data you've already seen. Now this is some interesting data here. Oh, you know what? I also wanted to change the maximum frequency to 1,000 for the tuning fork. Normally when a tuning fork's excited, it's excited by an impulse force, and then the tuning fork undergoes a gradual but exponentially damped decay. In this case, I'm driving the tuning fork at steady state. Now, I just made one mistake on this plot. The tuning fork is not acceleration in G. It was unscaled sound pressure. So I'm going to make that correction. I'm actually going to have to recalculate that. But in this case, I was actually driving the tuning fork at steady state. Well, how did I do that? Well, if you'll stay tuned for future webinars, you'll find out how I did that. So here's the time history. It's unscaled sound pressure. And we've got, well, 442 hertz. The program even tells us where the peak is. So, or we could use that data cursor, and we could take a look at where the peak was as well. So you can also use the data cursor method. If I can get the data cursor to work. 442 hertz. Now, the tuning fork was supposed to be 440 hertz, which is an A note, but of course there's manufacturing tolerances and so on, imperfections in materials and whatever. So it turns out this tuning fork is 2 hertz higher, 442 hertz, but for practical purposes that's no problem. It's close enough. So here's the phase angle. Again, the phase angle is really only valid where there's a non-zero amplitude. So at 442 hertz, at phase angle 0. But we don't really want to pay attention in this case to phase angle. So we could look at just the simple magnitudes. So we have unscaled sound pressure, frequency in hertz. Again, a spectral peak at 442 hertz. So that's good news. We're feeling good about our Fourier transform and its ability to resolve signals for measured data. Well, let's go to the drop transient. It's going to be external ASCII. In this case, it will be acceleration in G's. And we're going to look up to a frequency of 100 hertz. So I call this in. I got to click on external ASCII here. Drop.txt. Drop transient. Like a free bending mode. It'll take a number of seconds to calculate. Later on, we'll do this with fast Fourier transforms, which will greatly speed up the calculation. So what was the... Okay, here's the time history again. This is the drop transient. It's sort of like a free beam undergoing its fundamental bending mode. And again, we're not interested in phase, so I think I'll just skip over this plot. So here we have the spectral peak occurs at 9.573 hertz. So for that particular emission, that was the fundamental body bending mode for that launch vehicle and its payload combination. So what this tells us is if we want to avoid dynamic coupling, our payload natural frequency, its own natural frequency, as if it were mounted as a cantilever beam, should be 20 hertz or higher. We don't want it to be 5 hertz or lower because that could cause some other relative deflection, loss of clearance, and control problems. So we would want the payload natural frequency to be 20 hertz or higher to avoid dynamic coupling, to avoid control vehicle control problems. And that's per the octave rule, which is the rule of thumb. Okay. Then finally we got the channel beam. And the channel beam we looked at, it was interesting because of beat frequency. So let's call up channel.txt. And we're going to go ahead and calculate the Fourier transform. Okay, so interesting things about the signal. I think I'm going to call up a we'll get to leakage error a little bit later. So what we've got in this signal is an interesting signal. The spectral components, we've got one at 690 hertz. We've got 690 hertz, and this other is going to be 585 hertz. So if I go to Tool and Data Cursor, 585 hertz, 690 hertz. So let me go over here and I'm going to type 585 hertz and 690 hertz. Well, the difference is equal to 105 hertz. And this is what's called the beat frequency. And this is, I'm going to call this psychoacoustics. So our ears hear 105 hertz. If you were to listen to the equivalent audio of this signal, your ears would hear 105 hertz. So what do we design and test to? For engineering purposes, not 105 hertz. We do not design and test to that. Rather, we design and test to these two frequencies. So our avionics equipment, or whatever equipment we might have, our test article, however you want to describe your component, your subsystem, your system, your assembly, your subassembly, it needs to be, if it were to be mounted on this, and by the way, I should back up. This was a channel beam. And this was a channel beam excited by an impulse force. So if we had a piece of equipment that was mounted on this channel beam, it would need to be designed and tested for these two frequencies here. So that's just sort of some interesting things about beat frequency. Now, if you look at this amplitude modulation here, the envelope, so there's an envelope amplitude modulation. The amplitude envelope modulation is it's at the beat frequency. It's 105 hertz. But that's not what we design and test to. Okay, that's probably enough about beat frequencies. So what I'd like you to do for your homework exercises is go through these exercises yourself, back up to the previous slide and generate your own sine function. If you want to change the parameters, you can, or just use those ones. And then take the Fourier transform of your pure sine function. Then after you've done that, go back to these familiar files and download them and take the Fourier transforms of those as well. And just as a reminder here, let's see if I can call something up for you. I highly encourage you to go to the Vibration Data blog and visit this often. So if you go to it's vibrationdata.wordpress.com, and you go to this blog, you can download the webinar materials. So here I have the PowerPoint slides here. In a few days, I'll be posting this very audio-visual file that I'm creating as we speak. You can download these 3 data samples here. Then for those of you that like to dig into the theory a bit and find out more about the underlying equations, which we simply don't have time to cover in class or webinar classes, you can go to this link here for this case. And then if you just want to review previous webinar units, or maybe you've missed some because you had a meeting or you were on vacation or whatever, you can just, in fact, I already have a preview of what we're going to be covering next time. Next time we're going to be starting into leakage error, handing windows, and then we're going to be covering fast Fourier transforms. And depending on what kind of pace we can establish, this may take one or two webinars to get through that material. And then you can look up past things, Fourier transforms, random vibrations, sine sweep, sine vibration, natural frequencies, and so on. Then there's just a lot of other fun stuff at this blog as well. And then what you always want to do, and I constantly remind you of this, is each time I post a webinar link, I also post a link to the vibration data signal analysis package. So this is the main GUI package that we're using in this series of webinars. And you can download the zip file here and then just extract that to wherever your folder is. And then for convenience, you probably want to put your data files in that same folder. So I appreciate your interest in these webinars, and once again, thanks to Dr. Curtis Larson and the NASA Engineering Safety Center for making this all possible. If you have any questions, please contact me via email. You can, if you have any problems with the homework exercises, if you find any bugs, if you have any ideas for future enhancements, by all means, please contact me. And there's different ways you can contact me. One way would be, my email address is tom@vibrationdata.com. Actually, I have a number of email addresses that I make that a nice font for you. So tom@vibrationdata.com. Would love to hear from you. So have a wonderful day. Thank you, and goodbye for now.